Similar to Diffie-Hellman, the implementation of RSA is straightforward if you have a decent number library. Here I've got a Python script where I'm setting in bits to be 1024, and then I'm using a SymPy library to generate a random prime number between 3 and 2 to the n bits. So that gives me basically an n-bit prime number. I define n to be the product, p times q, and phi is the name that's usually used for p minus 1 times q minus 1. The last thing we need to do is pick a relatively prime number, relatively prime to phi, and so I'll use a helper function, random relatively prime here, which I'll show you in a moment. And then to find d given e and phi, I use a modular inverse helper function. We can double check here with an assert that the greatest common divisor of e and phi is 1, and similarly that e times d modulo phi is 1, which means that e and d really are inverses with respect to modulo phi. Finally, we take e and n and pair them together as a public key and keep d and n as our private key. We'll print those out, and then I have an example plain text here that I turn into a ciphertext by doing the modular exponentiation of plain text to that public key's d modulo the n that's in the public key. And then we should be able to see that if we decrypt it again using the private key, then we get back to the original plain text. Alice could also use her private key to sign the plain text, and then someone using the public key could decrypt that and make sure that it really was from Alice. If we run this code, then you can see that it took just a little bit of time, but we generated this public key with, this is the E part here, and this is the number n, and the private key has d and the same number n, and all of our asserts passed, which means that our ciphertext here could be decrypted back to the plain text, which was that 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 message that I started with. The ciphertext number is very big because it's close to n. The plain text could have been big of a similar size, it just happens that I started with a small number. But good encryption will of course map even a small number into something in the larger range of bits. And here, by the way, are those helper functions, random relatively prime, just is looking for a random number whose GCD is 1, and here's modular inverse code.